Good morning. There's homework due today. It looks like I hadn't looked at the numbers this morning, but when I looked last night, I guess it was technically this morning. I was having some back and forth with a couple of you on this, who are once again doing this at the last minute. That's a way to do it. It looks like most of you got this in. That's good. So the task was to visualize the structure of the program. In this case, we're just going to build a graph, and we can visualize it using the graph viz tools. And I thought this was fairly straightforward, and it seems like for most of you it was. Blocks flow into another block because they just run directly into that block, because they jump to a block, or because there's a loop or a conditional branch, etc. And you would produce a graph that would end up looking something maybe like this, or maybe a little more complicated. So the idea was to be able to produce a graph for a program. I gave you a sample program, and you should be able to build that and then generate the graph out the other side. And ideally, it would look something like that. It should look almost exactly like this, except the order of the arcs might be different. You could write it to a dot file, and you could use dot to convert it to a PNG. I have the fear that's going to open GIMP, but I guess I'll just live with it. And it is. That's why you never install GIMP. And you should wind up with a graph, something like this, which shows how the basic blocks flow into each other. And then there's this little called function over here that's not directly linked. All right. There were a few things that were noteworthy that I mentioned last time about the little example program. The little example program has lots of special cases in it. I think I have blocks in this folder. I do. And so here's the entry. We have a jump above or equal, which, as I talked about last time, is actually an opaque predicate. It jumps to 1159. So really, you're jumping to here. And this is the true block that is present in that in the program. If you don't recognize the opaque predicate, then you're going to just flow forward and see this as the next instruction, which is a jump if equal to 11.9e. And so you're going to think there's a block, there's a break between this in this code right here. You identify this as a block leader, and so this block will just end right here when it encounters the next block leader. And if you then proceed on to the data bytes, you'll see a jump greater than A2. And again, you'll want to split the code at A2, which happens to be this trailing return here. And so you'll split this last block even further by breaking the return out. And those aren't necessary. That's just the way that it ends up. Another side effect of this is that the address is after each one of these. So this is the one after this one. This is the one after this one. What comes after this? Well, there's a little bit of trickery here, right? This isn't really the correct interpretation because of the opaque predicate. This is one way to interpret these bytes, but it's not really the code that's going to run. And as a result, this little 2-byte instruction, 59, 5A, leads me down to interpreting it the next block this way. And so I wind up with 59 and 5A both in here. And those could both be executed, right? You could actually have code that does that. The difference between these two, of course, is that I've chopped off 1 byte, and that 1 byte is a prefix byte, which tells me to use 64 bits and RAX instead of using 32 bits and EAX. But there you go. So after that, they're in sync, which is if you're trying to hide code, that's what you want. and you'll want to be, judicious about how you use prefix bytes. The end result of this stretch of code and this stretch of code are almost the same, except here we're loading a quad word from memory, and here we're loading a double word from memory. And that's the kind of thing which seems innocuous, but is exploitable. You can use that to, once again, trick the code analyst and do some nasty stuff. Then we flow into this block, and it's split by the loop 1180. So we come back up here, and we just repeatedly iterate on this. We have 11A3 here, which is the subroutine we're calling. This would all be one block, if not for the false starts up here. And we come to 11A3. 11A3 is this little subroutine right here that does the stuff we would normally have done in the body of the loop. So nothing too elaborate or fancy. Not all of the code that is called appears in here. For example, this ends with 11AC. And we see up here, we call 11B0. Why is 11B0 not present in this listing? Shouldn't it be? It's called, it's a basic block leader. It's not in the text section, right? It's in the subroutine section. And so we wouldn't expect to see it here. All right. So I think that was, I don't think people were too confused by that. I think it looks like you all did a fairly good job with this, and that's good. I will post my solution, which, so I'll go back. I'll post my solution, which is going to look a lot like the previous code that I wrote with a few little changes. So I went ahead and changed a few things in here. Populate cache no longer has a limit in it. It just runs through all the instructions. I found in testing this is way faster to do this, and so I just do that. But really, the thing that costs the most time overall is calling this guy. And so if we can avoid calling it, the more we can avoid calling it, the better. And restarting it. So if you just iterate, that's low cost. But if you have to call it to start out building the generator, that is a very costly operation. So I think all that looks the same. I do have something new in here. I have a new class called block. And if you stare at this for a few minutes, you'll realize there's a from address in here that's going to build a block, basic block object from an address. And this is exactly the code that I used before that was, I think, called get basic block. Just packaged in here into a method in the code. Returns a basic block to me. And the interesting thing about, let me scroll up just a little bit. The interesting thing about a block is it's going to have the block instructions, but it's also going to keep track of the possible next instructions. And that's just handy for building the graph and doing other stuff. And it's pretty simple. I just come in and grab the instructions and put them in the block. And then I go ahead and add the next and the branch address if they're provided. And that's how you initialize a block. And you can see it being used up above in the get from address. And then get instructions, get next address, get branch address. Write it out as dot. I just made that a method in here. It seemed like a good place to do it. So I write out the block address, and then I write out the arcs. If it has a next, I write that out. If it has a branch, I write that out. And then I can give you back, I can turn block into an iterator over the instructions by giving you back a generator through the iter method. And that will work. And this is maybe a little overproduced, but there it is. Find main, no changes there, except that it now uses the block from address stuff to get the block. Pass one, no significant changes in here, except that once again, it uses block from address to get the block. And pass two also uses block from address. Pretty simple stuff, and this code didn't change at all. All right. Let's talk about satisfiability. And to get there, let's take maybe a bit of an odd road. Let's talk about decidability. We've talked about it a couple times. We're going to talk about it again. And we're going to talk about the hailstone numbers again. They're just a great example. for this kind of thing. Once someone solves this problem, I have to find some other thing to put in here. So if you remember, the Hailstone numbers say that given an integer, we define a sequence of integers to be, if n is odd, we multiply it by 3 and add 1. So if n was 7, we'd multiply it by 3 and get 21. Then we'd add 1 and get 22. And that would be the next. So 7 would be followed by 22 in the sequence. If n is even, we divide it by 2. So if we got 22, the next time around we'd get 11, which would be odd. We'd multiply it by 3 to get 33 and add 1 to get 34. We divide it by 2 and get 17. And so on, around and around and around until we hit 1 and we terminate, right? Because at 1, nothing new interesting happens, right? 1 is odd. So I take 3 times 1 plus 1, which is 4. I immediately divide by 2, divide by 2, and I'm back at 1. And I just repeat that little cycle. So there's something called the call-outs conjecture, which a lot of people have worked on way too much. It's one of those math problems that tends to destroy careers because people spend their entire careers working on this problem and making very little progress because the problem is deceptively simple and ridiculously hard. So the call-outs conjecture says this sequence terminates for any positive integer n sub 0. So anytime I put a positive integer in this, I'm eventually going to get down to 1. And the sequence number is just a Hailstone number. So if I start at 23, right, I multiply it by its odds, I multiply it by 3, and I get 69. I add 1 to get 70, divide by 2 is 35, multiply by 3, get 105, plus 106, and so on down the line. And so here's some Python code to compute and print the Hailstone sequence for a given integer. So with all that in mind, here is a little C program, and you give it a start value. While start is not equal to 1, we see if it's odd, and we do the time 3 plus 1. Otherwise, it must be even, and we divide by 2, and we just run this way until start gets to be 1. And so an interesting question is, does this program terminate for all inputs? Well, if someone could prove the call-outs conjecture, clearly the answer would be yes, it terminates for all inputs. But the call-outs conjecture hasn't been proven, so we don't know if all of the integers eventually terminate at 1. So the question is the question of this program's termination decidable? So this seems like applying the halting problem, asking if it terminates for all inputs. I'm asking it about a problem that is an open problem. How do I deal with this? Well, it turns out that we have to think about a few other things in order to think about this correctly. Here's a little harness program that maybe reveals some of what's going on. So if you compile this and you link it with the little Hailstone thing, you can run it, and it'll start at the value 1, and it'll run up to some limit. And in this case, we've got a 16-bit limit, and try the Hailstone for that. And so if you run this with the 16-bit limit, it will terminate almost immediately because all of the 16-bit numbers terminate. And we've known that for a long time. This is not new information. So all of those, all 65,535 of those, because we don't do 0, terminate. What if I try it for a 32-bit integer for all of those? Well, if you run that with 32-bit limit, it will take about 47 minutes on my desktop machine right here. It takes about 47 minutes. If you do the math to figure out how long it would take, assuming a few things about the sequences, a few things that are normally assumed about the length of sequences. And you can go find the literature, and there are people have proven theorems about lots of other stuff around this. They just haven't proven the main one, the main result, which may or may not be true. We don't know. if you do the math on that, it turns out to do all 64-bit integers on this machine here would take about 393,000 years. So I have not run all these. I've not done it. I don't plan to. It's a long time, but it's still a finite amount of time, right? It's still a finite amount of time. If you can keep your computer running for that long, then you'll know the answer for all of these, but not for all numbers, of course, right? Because this is a vanishingly small subset of the infinite number of positive integers. What if I run this? I'm running this for I'm running it for 393,000 years. I get to year 394,000 and it hasn't terminated. Do I keep waiting? I mean, this is based on some assumptions and averages. Maybe I'm just wrong. How long do I keep waiting to see if it eventually terminates? Well, it turns out this is decidable. It's basically a very large finite state machine because there is nothing in here that makes this a general Turing machine. You have to think about that for a few minutes. A Turing machine has unbounded storage. It has that tape, that unbounded tape. This doesn't have that. It basically has this integer, which is a fixed number of bits, and it manipulates it, and that's all of it. So it's basically a giant finite state machine. I mean, it's huge, right? 2 to the 64 minus 1 is a big number, but it's still a finite number of states. And the state is completely bottled up in the number start. Okay, that's it. The state is totally bottled up into that. When I call Hailstone, I do math, but I manipulate this until I get done. And so the state's really just bound up in this 64-bit integer. And so at any time, if I stop the program and I record the value of that of start at that moment, I have everything I need to know to then continue the program later on. So it's really just a finite state machine. And so with not much memory, this didn't take much memory. It just takes a long time. I would eventually get the answer. So it's decidable even if it's not practically decidable. So why is all this relevant? Well, it turns out that most things about most programs are decidable. Most things are decidable. Not everything, of course, and not, I mean, again, there's an infinite array of things that are undecidable, but a lot of things about most programs are decidable, right? Interesting things about all programs, now we're in the undecidable class, right? I can't just give you any arbitrary program and some non-trivial property, because then I run headlong into Rice's theorem, so I can't do that. But I give you a particular program, and I ask you a question about it. Even a sophisticated semantic question about it, and you should be able to answer that question. It's hard to write a program whose termination is undecidable, right? It's easy to write one that doesn't terminate. That's easy. Probably all done that. But to figure out how to write a program whose termination is undecidable is pretty hard. The Collatz conjecture is really close to that. Right? The Collatz conjecture is a conjecture whose answer is unknown. And the general Collatz conjecture, there are people who think it may be unprovable. In fact, there's a strand of thought that it might be provably unprovable. Nobody could prove a theorem saying I can't construct a proof given the tools I have available now. And that's been done, right? People have proven that, for example, with the tools of piano arithmetic, I can't prove certain theorems. It may be provably undecidable whether it's true. That's an interesting thought. But even given all that undecidability and unknowability and all of that, this little program still turns out to be decidable. And I think that's kind of interesting. So let's go in a different direction, still thinking about program termination, and we're going to revisit program slicing. So here's another little program that does some stuff. It shouldn't look too elaborate. It's in assembly because we should be looking at lots of assembly. So I zero out EAX. I put start, whatever that is, in RBX. What is start? It's a constant defined up here, and here it happens to be 1. So I put 1 in RBX. I have a loop here. That's interesting. I add a stride to RBX. I then increment RAX. So each time through the loop, I'm going to increment RX. I start out by setting it to 0, and I'm just going to count the number of times I go through the loop. And I compare RBX to the end. What is end? It's 701. So each time through, I'm going to add 7, and eventually I'll add it 100 times. I'll get 701. The comparison will succeed. I will not do this, and in fact, we'll just terminate, returning the value 701. So that seems like that would work. And I think that's it. There it is. So we'll build it, so that will assemble and link it, and we can run it, and it just immediately terminates. We didn't show the result, but it turns out you go through the loop 100 times. That makes sense, right? Each time through, you add 7. You add 700 times. You've added 700 to 1, and you get 701. Nothing too crazy there. We can make a little change to it. So what if I change this to 703? How about that? Well, it's not 100 anymore, right? Because 100 sevens is 700. I add 700 to 1, I get 701. That misses this. It's a 64-bit integer, so it's going to take a while to go around again. And so let's build it again. And let's run it. Is it going to terminate? How would we know if it's going to terminate? Right? I mean, how would we figure that out? Maybe I'm just not waiting long enough, right? Each time it's counting up by 7. That's an odd number. The thing that we're trying to hit is itself an odd number, 703. Eventually, the 64-bit integer will overflow. That's going to take a long time. It's going to take a long time. Even counting by 7, it takes a while because that's a big number. And so maybe the next time it comes around, it'll be, right? It will be equal to 703. And so really, I'm asking a question about modular arithmetic. So figuring out whether this program terminates really is a question of, do we ever get past this branch? Right? Does this branch ever fail, and we then fall into this case and we just slide right through and terminate? So we can reduce the question of termination to a simpler question way, which is there ever a case where we do not take this branch? Well, this branch is jump if not equal, right? If not equal, I'll jump up here. So that means if the 0 flag is clear, I'll jump up here, right? If the 0 flag is set, I'll come down here. So really, we can reduce this to saying, well, the 0 flag must be set right here. That's what we need to terminate. We need the 0 flag to be set. How does 0 flag get set? It gets set when RBX and end are the same value. So we can slice backwards, right? This depends on the 0 flag. The 0 flag is set here. It's an L value here. So I need RBX, right? Which is an end, which are R values here. And so RBX goes into my set of things I care about. Here I'm incrementing RAX. That's not RBX, so I don't care about it, and I can ignore it in my slice. Up here, RBX is being set. It's an L value. It's one of the ones I need. So sure enough, I need this line too. And then this is the label for that line. I walk up here, RBX again, an L value. So I need this line too. I move up here, doesn't mention RBX, just mentions the X. I don't need it. So I do a slice. I'm slicing backward on ZF from here, and I wind up with these 4 instructions. Should be clear, slicing is a basic technique that you should understand. And so here's a fragment of it that is only concerned with when this loop terminates. We call this, right? This is the slice of the code that controls the program flow. We call this the control slice for the loop or the program. This is the control slice. And it's simpler, I think you'll agree, than the whole program. We've thrown quite a bit of stuff away and wound up with just this. I probably should have kept the definitions of these, but it doesn't matter. We're going to change them as we go forward. In fact, let's just shorten them. T, S, and E. So start, stride, and end. If we make them like this, it's easier to write equations about them. And so we need to know when RBX is equal to the end. Initially, RBX is T, right? We just set it to T up here at the start. The loop body executes N times. If we say it executes N times, then we add S N times. So we add NS to T. And we'd like for NS plus T to be equal to E in a 64-bit field. And so what that would look like is this little equation down here, right? T plus N times S congruent to E mod 2 to the 64. If we have this, this tells us that our program will terminate after N iterations. Or our program maybe would have terminated after N iterations. Think about this, right? If our program terminates after one iteration, then this is met and we're satisfied. But there might be other values of N that satisfy this equation. This equation doesn't say anything about the sequential nature of the program. And really, it doesn't say anything necessarily about, it doesn't know about termination. So it might be that N's a perfectly valid answer for 1. And another valid answer is, let's say, 2 or 14. Those could all be valid. Any N might be a valid answer to this. Something to think about, right? My T and my E might be equal. My stride might be 0. It doesn't matter, right? I go into the loop and I immediately terminate. So the correct answer from our point of view, thinking about this as a process, is N is 1. But N is 2 or N is 3 also satisfies this equation. So I have to keep that in mind. So we know the start, we know the stride, we know the end, and we want to be able to find an N that makes the above true when the loop halts. And if we can't find that, then maybe the loop doesn't halt, right? Maybe it runs forever. So another way of saying this is the program terminates exactly when there exists an N such that 2 to the 64 divided by this. So is there a value of N that satisfies the equation? And even better, it would be great if there were a program that could find that value for us. So keep all that in your head too. Let's think about satisfiability, right? We'd like to have an N that satisfies these equations. So satisfiability. So you probably studied satisfiability in your computing theory class, or you should have. And you may vaguely remember satisfiability. So here's a quick primer on satisfiability. Given that we have a formula, right, just a set of logical connectives and variables and logical constants, right? True, false, P, Q, and R, and then things like disjunction and conjunction. Given a formula, is there some model? What's a model in this case? An assignment of values to variables. Okay. Is there a model that makes the formula true? If there is, the formula is satisfiable. Otherwise, it isn't. If all models make the formula true, then the formula is valid. So a lot of words to explain something that we can maybe explain a little better by giving you some examples here at the bottom. This first equation is valid. So a model in this one would be an assignment of true or false to the only variable in this, which is P. So if I assign true to P, not P is false. So it's false or true, which is true. If I assign if I assign false to it, then not P becomes true, and I have true or false. So either way, I wind up with true as a result of this. There's nothing that I can assign to P that will make this false. And so this is a valid equation or a valid formula. How about the next one? Here I have P and not P. And you could, since you know about the excluded middle, you can immediately see this is not going to be satisfiable, right? Anything I plug in for P, no matter what it is, this will be false. If I plug in true, I have true and false, which is false. If I plug in false, I have false and true, which is false. This whole thing is an invalid or not satisfiable formula. And of course, there's the in-between. Over here, I have P implies Q, and I know that this is satisfied by any model, okay, that assigns false to P or true to Q, right? Any of those would work. I have two variables in here. I can assign true or false to either one, so I have 4 possibilities, and you know, a couple of those are going to make this whole thing. 3 of those are going to make this thing true. 1 of them will not. So this is in fact satisfiable. So in propositional logic, where we just have variables and truth constants and logical connectives, like you see right here below, but no quantifiers, satisfiability is decidable, which is great. It may not be easy, but it is decidable. We've already figured out that decidability doesn't mean easy, right? We've already figured that out with the previous examples. Decidability can be really hard, but it is decidable. Decidability is a good thing, because the alternative is even worse. In first order predicate logic, where you have quantifiers, satisfiability is not decidable. And again, that's because we've introduced this notion of quantifying over a set, and we can actually play some tricks to have that wind up looking like the halting problem or something else, and demonstrate that we can't decide it. So Boolean satisfiability, SAT, is the first problem that was proven to be NP complete. In fact, some of you may have had state and proof SAT on an exam. If you did, you have my condolences. I once had state and proof 3 SAT on an exam, and that was not fun. So what do you mean by NP complete? You should know what NP is and what NP complete and NP hard and so on, and sufficient and all those things mean. Polynomial time reducibility, you had a computing theory class. You can check it by plugging in the answer, so it's easy to check. Finding it may require that you enumerate all the different models, and there could be, 2 to the n of those models, so it's exponential. So you might have to look through an exponential space to find the answer, but it's easy to check it. That's kind of the definition, right? That is the definition of NP complete. So SAT solvers exist. That's a thing you can go and find and download. And most of them work by converting Boolean expressions to what's known as conjunctive normal form, or CNF. So here's a little predicate, a little formula. We have not P or not Q and R. And we want to convert this to conjunctive normal forms. So we want to have ands in here and ors in here. And we can do that, right? We just apply the distributive property, right? This is not P or not Q, and not P or R. And that's what we get, not P or not Q, and not P or R. So there we go. Once we have it like this, we have kind of an easier task, right? I have to then prove that this is satisfiable and that this is satisfiable, right? And if I can find the model for this and find the same model applies here, then I'm good. So basically, I'd build a model to satisfy this, and I would then check it on this one and check on any other clauses that were here. And if it passed all of them, then it works, and I can return it. if I have a model here that doesn't work, I have to try the next model here. So I need a way of enumerating the models and then testing them. And in fact, you can do that. So you just find an assignment that makes all the individual clauses true. And there can be multiple solutions. And in this case, for this little guy, there are. And some of them are listed down here off to the side, right? If P is true and Q is false and R is true, true, right? False, true. So true here becomes false for this. False or something is just out of the thing. So we're left with this guy. Q is false, so not Q is true. And R is true, so true and true is true. So the whole thing becomes true. And in fact, Q could be false, and that will work if they're basically all this way. And of course, if P is false, this is going to be true. So the whole thing is true. So you can check all those. Which one of these solutions will a stat solver give you? Will it give you all of them? Probably not. It's going to choose one. It might be random, and it might vary from run to run. Some of these use randomization to seed their start. The idea being that the amortized time for the solver to run is faster if I randomly pick a starting point. Because of that, some allow specifying a random seed so you can get a repeatable result. And the thing to keep in mind is they give you a solution, but they don't necessarily give you the solution, right? Earlier we talked about the number of times of the loop, n, and the things that would solve that equation. There might be many values of n that would satisfy that equation, but the only one we cared about was the smallest one, because that would be the number of times the loop would run before terminating. So there are lots of stat solvers in the world. A few of them are Minisat and Glucose and Ling Ling. There's 3 that are widely used. And if you don't want to think about all that, you can think about PySat. So PySat is a Python interface to a lot of different stat solvers, and it includes these 3. So if you wanted to run one of these, just go get this, and you're in pretty good shape. And the interface to it is a little weird. It uses signed and unsigned integers to specify what's going on. Remember, we just have Boolean values. So let's say we have, let's say we call them all P and we subscript them, right? There's P1 and P2 and P3. That's the set of variables you have. And you can negate them. And you can OR them together, right? It's going to be in conjunctive normal form. And so it turns out that what that looks like is if I want, so I can pull this up, if I wanted to have like not P or not Q, oh, no, let's see, not P1, there we go, or not P2, then I would write that as the pair -1, -2. And that's just how the interface works. So it's a little bit tricky, but nothing too elaborate. And you can grab those and play with them. That's all well and good. There's lots of good uses for satisfiability solvers out in the world. But let's get a little bit different, and let's talk about satisfiability modulo theories. So satisfiability is just fine, but we're just talking about these Booleans. And you remember earlier, our question was about an integer that satisfied a modular arithmetic formula. And it's you could write, it turns out you can, in fact, shoehorn that into here, but it's hard, right? You have to basically invent numbers out of this and a way to represent them, and a way to represent math on them, and a way to represent modularity and residuals. And that just, no, you don't want to do that. So what we might do is start with a satisfiability problem like this. And then we come along and we replace something like P with a statement out of a different theory, like a theory of integers. And that would look like X is greater than or equal to 15. Okay. And we call that a background theory. Okay, these are called background theories. So in this case, it's some theory of integers, right? It's something that is strong enough to include this, which could be all the way up to full arithmetic, or it could be some limited forms of arithmetic. It just depends. We might leave these as they are. So not Q might stay not Q. But again, over here we have P, and so we replace that again with this. And so now we have an expression that involves some Boolean variables, logical connectives, but also can involve numbers, right? This thing is really just a predicate. It's going to be, it's our P. Our P is actually this, and it's going to be something that's true or false. In terms of finding a way to satisfy this, if we satisfy this, it'll tell us, do I need P to be true? If I do, then X has to be greater than or equal to 15. I have to choose an X that fits that criteria. Do I need P to be false? If I do, I have to choose an X that's less than 15. All right, so this is telling me something about this. So we solve the outer problem, which is the satisfiability one, and that gives us a set of inner problems to be solved inside those theories, right, about numbers or strings or what have you. And so we call this, and it constrains these, so we call this satisfiability modulo theories, or SMT. And there are decidable theories like Pressburger arithmetic, right? This is greater than or equal to, this could be a statement in Pressburger arithmetic, which turns out to be decidable, or it could be not decidable. And then there are many theories that might be really useful for us in the CS context, like theories about arrays and bit vectors and lists and other common kinds of data structures that we encounter. And so it'd be great if someone built a tool that took a SAT solver, which we know exists, and maybe a general constraint solver, which we know exists, and plug those things together to give us a tool to be able to do this. And in fact, as you probably already know, there are such tools, and one of them is Z3. So Z3 is an open source satisfiability modulo theorems solver written by Microsoft. Okay, it's just how it is. You can install it on your Linux system with pip3 install Z3 solver. That'll install it. It'll install the pieces that you need, and it'll give you a nice Python interface to it, which we'll look at in just a moment. And if you want to read about it, you can head here. So the whole stuff is up on GitHub, and you can read the guide and their examples, and there's a tutorial and a bunch of other fun stuff about it. Don't be put off by the fact that it's Microsoft. This is actually a really, really awesome tool. So we can try a small problem in Z3. We have not P or not Q and R. And so how would we code that up in Z3? Turns out it's not that hard. We have 3 Boolean variables. So I declare 3 Boolean variables. I declare a Boolean named P, and I assign that to the variable P. Same for Q and same for R. So now P, Q, and R are literally Boolean variables. So I go get a solver instance, just like this. And remember, the solvers take things that are in conjunctive normal form, but they're smart enough to recognize and convert some things that you give them into conjunctive normal form, into additional clauses. So I can call add as many times as I want to add a clause. But if I add a clause like this, right, this is not in conjunctive normal form. But when I add it, the system is smart enough to figure that out and correct for it. So how do I write this? Well, it says not Q and R. Well, right there it is, not Q and R. So a little bit funky, right? This is a little bit of prefix notation. And then not P, and I OR those together. So there's my constructor for that expression, and I just add it to the solver. Once I'm done adding everything I want to add to the solver, and all the things that I add have to be simultaneously true for the solver to be, for the system to be satisfiable, I can check it. So running s.check tells me if it is satisfiable. And so it'll give me back the answer. It's satisfiable or it's unsatisfiable. Unsatisfiable is a tricky answer. It could mean the system was not able to find a solution, not that it's completely unsatisfiable for reasons we've talked about. But if it says it's satisfiable, that means it found one. And so we can print the model, right? The model is the assignment of values to variables. We can print a model that satisfies it with this line right here. So there we go. This will run through and give us an answer. And I think I have that code lying around in this folder. And there it is. And so I can run that. And it says no module name Z3 because I haven't installed it on here. Pip3 install Z3 solver. Because this computer had trouble until just this morning. And there we go. So installed. I told you it was not hard. And so now we'll run this and it says, hey, it's satisfiable. And look at this. P is false, Q is false, and R is true. Will that work? False, false, true, C. Oops, let's go back. False, right, makes this whole thing true, which means the whole thing is true because true or something else is just true. So yeah, that works. And in fact, over here, we get an answer. It says it's, the check says it's satisfiable. The model gives us, oh, it gave us the same one. No guarantee that may be the case, but in this case, it seems like it was. So there we go. Simple use of Z3. But this is all Boolean stuff. There's no integers in here. So before we get to looking at integers and stuff, I'll mention that there is a standard language for SMT solvers. It's called SMTlib. It's actually on version 2 right now, I believe. And you can read about it here. If you want to work with Z3, but you're afraid of installing software, why that would be, but it could be, you can get to it online right here. And there's a tutorial up here at this site. And in fact, if we go here, we'll get to an online version of it. But what you'll put in here is not the Python stuff you saw. What you'll put in here is SMTlib expressions. And those look like this. They look like Lisp. So if you're not familiar with Lisp, it's a untyped lambda calculus based language, which is one of the oldest. It's debatable whether it's the oldest high level language. If Tim were here, he would yell at me to tell me it definitely is, and here's why. And if Kirk were here, he would yell at me to tell me it's definitely not, and here's why. They both make good points. Neither one of them is here, so I'm just going to say it's debatable. They're probably off somewhere right now yelling at each other about this exact question. So what I do here is basically the same thing I did in the Python, just the syntax is a little different. So I declare a constant P as a Boolean, and a Q and an R. So this creates 3 Boolean variables. It says constant, but I mean, again, what are these things? They're just things that hold a constant Boolean value. And then I make an assertion, and I can have as many assertions as I want, but in this case, I assert that not P or not Q and R is true. So I assert this to be true. And then I can check it with checksat, and I can get the model with get model. And so there you go. That's a, not super sophisticated piece of code. Looks very much like what we saw before. I'm going to grab it and I'm going to head here. See if the internet works. Yes, it does. It's got an example already in there. We're going to paste in our example, declaring these 3, asserting something about it, checking it, and then getting the model. We execute it. And we get back sat because we explicitly asked to check it. If we took this line out, we wouldn't have this sat up here. And then we get back the model also expressed in Lisp. And so the model is Q is true, R is true, and P is false. There you go. The difference between maybe worrying about constant versus fun. Again, feel free to read the documentation. I don't think I need to go through all of that with you. I don't have time for that even. But there you go. So you can play around with the SMT lib2 over here. And, or you can just do it in Python. It's up to you. All right. Can we use all of this? Can we pull all this together and use Z3 to solve termination? Well, again, you've probably had it beaten into you that you can't solve the halting problem and all this other stuff, but of course we can. So we came up with this, right? We said that T plus N times S minus E was 0 mod 2 to the 64. And if this was true for given T and S and E and some N, which we don't know about, if we can find an N that satisfies this, then it must be that the program terminates either after N iterations or before N iterations, right? We are not guaranteed it's the smallest N. How do we write that? We could write it like this, right? Declare fun in int, T int, S int, and E int. So we declare these as integers. And then we add constraints. How do I make sure that I know that T is 7, S is 4, and E is 22? I just assert those things. So as part of my set of assertions, I say T and 7 are equal, S and 4 are equal, E and 22 are equal. And I assert that N has to be greater than 0, right? Because I have to go through the loop at least once. So that's my first part. And you can see I'm already using background theories, right? I'm using some information about integers in here. And I've picked the theory by specifying this. I have told you I want to use ints, and here they are. I did not tell you I wanted to use bit strings that are 64 bits long. I told you I wanted to use integers. We'll come back to that in a moment. So because of that, these aren't bounded. I'm going to need to do some modular arithmetic, and there it is. So what I'll do is I'll take N times S. I will add T and subtract E, right? So if you're not familiar with Lisp, this may be causing your brain to hemorrhage, but this makes a negative E. That's N times S, that's T, and then I add all three of those together. And this is the first atom of a first argument to mod. The second one is this, 2 to the 64. And so I mod this value with 2 to the 64. And what I'm concerned with is when this thing equals 0. And so I have a 0 and an equal here. And I close all the parentheses, and there's my assertion that captures this little equation right here. This captures constraints about T, S, and E. This captures an interesting piece of information that I better not forget about N, or I might get a negative value or 0 or some other weird thing, which doesn't make sense to me. I need this. Here's the little constraint about the termination condition. And then I can check it and see if I get back a model. And in this case, let's pop out of here, take my word for it. Let's grab all this. Wait, did I lose the focus? I did. Let's grab all this. Oops, go back to doing the wrong thing. There we go, back to here. Paste it in, and let's run it. Let's see what we get. And what we get is it's unsatisfiable. And line 18, column 10, model not available, because when I tried to get the model, this is line 18 down here, there will not be a model. So I get an error here. So it ran and said, nope, it's unsatisfiable. Right? I didn't find a way to do it. So in this case, we could reasonably conclude program is going to run forever. And in fact, because of some things that we know about proving things about modular arithmetic in this way, it's certain the program will run forever in this case. So We better not choose our start to be 7, our stride to be 4, and our endpoint to be 22, or else it will just never, ever, ever terminate. Well, what if we change E, the endpoint, to be 23? Well, we can code it up in Python like this. So here it is in Python, and I just import star from Z3, and then I have N be an int, and T be an int, and S be an int, and E be an int. I make a solver. I add the same things I had before, but notice the double equal to this Python. And then I add the N greater than 0. And this looks much nicer, right? I have T plus N times S minus E percent of modulo 2 to the 64. And that's how you write exponentiation in Python. And I want to know when that's 0. And then I can check and print the model. And I think I have that. Yes, I do. I have it lying around in a file over here. And so let's run it. And I get back an answer, right? I get back T is 7, which I knew because I required that. S is 4, which I knew because I required that. E is 23 because I required that. And N is 4. That's great because that also happens to be the smallest. I happen to know that's the smallest answer. And so that's pretty handy. That's not what I got when I was making the slides. What I got when I made the slides was that value for N, which is not 4, starts with a 4, but it's a really big number. And it turns out this is a perfectly valid answer to the question. It's just not the most interesting one. It's not the smallest. But it does tell me that because there is a value for N, this will terminate. So I've now grabbed a tool from Microsoft, written some Python, and proved termination of a program. And so I did point out the 4 works here, which is what it gave us, right? 7 plus 16 is 23. And so that's our endpoint, so we're good. Well, this works. If I can prove termination of programs, right, against everything that we had been telling us, then I could prove all kinds of neat stuff. So I found named Byron Cook, created a tool called Terminator, which I think you have to read in a loud voice because it's in all caps, to prove termination of programs. And we can reduce lots of interesting problems to termination. For example, if a correct password is entered, the program terminates. So the termination condition, if we can derive the termination condition for that case, we'll be given a password that will work. That's nice. If a particular string is printed, the program terminates, etc. So Terminator tried to find a well-founded relation on variables of interest to prove termination. That's what we just did. A well-founded relation on variables of interest. If you want to see a YouTube video about it, go here. He'll tell you about Terminator. Terminator did not survive. It was destroyed at the end of the movie, and along came T2, which you can find on GitHub here. Right, that's the one that's made out of living metal, I think. And so it just continues to advance and grow, but now there's a bunch of other tools in the same vein that do some of these same kinds of things, let you reason about what a program is going to do. And again, right, I want to know what a key is to access something. I want to know if a program ever does a certain operation. And I can treat that as a reachability problem, which I can then solve by looking for termination under that condition. So far, we've talked a little bit about when things are decidable. We figured out that termination can be decidable. We figured out if you can write down the conditions for termination, you can plug it into a tool like Z3 and maybe get an answer that tells you whether it terminates or not. And that may not seem like an interesting answer until you couple it with something else that you want to know, and then it can become, pretty interesting. It lets you find out something interesting about an otherwise unknown program. So when you start analyzing a piece of code, trying to reverse engineer it or do something else with it, often there's this initial challenge of just finding an anchor, right? Anchoring somewhere in the program, finding out something the program does, and understanding where that's located. And because then you can find other things in relation to that. For malware, for rootkits, let's say, often that's trying to find the command and control. If you can find where the command and control dispatch is in the program, everything flows from there, and you pretty much cracked it at that point. So there's this, how do I find some of these things? Right? How do I find these things? And one way to do this is to basically treat those as termination conditions and then try to prove something about the reachability of that state. This is really, we're talking about termination, but it's really reachability analysis. It's a whole other category of things that I don't want to get too deeply into. But how do I get those expressions, right? The way I got it for that toy program was I sliced on the control piece to get the control slice. I turned that into an equation and then prove something about it. But is there some way for me to automate that process? And there is, and it's symbolic execution. So we're going to talk about a few different kinds of execution here, eventually settling on something that might be of a bit of use. And I'll be right back. And I'm back. Sorry about that. So concrete execution is pretty easy to understand. Concrete execution is what happens when you run a program, right? You've executed the program concretely. And you can observe the program's behavior for the specific case that you run. And you need to do things like, if you're trying to be systematic about it, you need to have things like proper experimental control, right? If you're running your program and at the same time on the same machine, you're loading up a web browser and opening a bunch of the tabs, and that's not part of your experiment, it can influence what your program does and how it behaves, right? I mean, a number of things might happen from running out of memory to the web browser taking down part of the machine. Who knows? So you need to have experimental controls, and that can make a concrete execution repeatable. So over here on the side, I got a little program, and we'll take a look at this in just a moment. So how long would it take to find the error in this program? And the role of the error is being played by this assertion right here, assert 0. So I assume, perhaps incorrectly, that people use assertions in your C code. Probably should be. In this case, you assert something, and if the thing you're asserting is true, then you're good. This just plows right ahead and doesn't do anything. Here we're asserting 0. Well, 0 is false in the world of C, and so this is going to cause an exception and terminate the program. Okay. And so here's my super complicated program. It's called F. Great name for program. It takes 2 arguments. I multiply y by 2, that's z. I then check to see if x is 100,000. If x is 100,000, and if x is less than z, then I have this assertion happen. Otherwise, I don't. So if we just randomly generate x's and y's and plug them in, how long will it take us to find this bug? Right? If I just fuzz it, how long will it take? Well, extreme values won't work because I could plug in the extrema for this and I won't hit that. It might take a little while. There are 2 to the 32 int values because I'm using ints, not 64-bit integers. Exactly one of which is 100,000. So that's 1 out of 2 to the 32. What about the inner test, right? This guy. Well, there are about 2 to the 31 minus 100,000 values of y that will work because of the overflow, depending, right? Why would I say y? Because z is twice y. Right? That's why we lost one of the bits on the exponent. 100,000 is reasonably small with respect to the value 2 to the 31, right? This is a small number compared to that number. How big is this number? Well, 2 to the 10 is about 10 to the third. Okay, so this would be 10 to the third times 10 to the third times 10 to the third, which is 10 to the ninth, right? Which is, right, 10 to the sixth is a million, 10 to the ninth is a billion. And I have one other bit left over, right, 31. So it's about 2 billion. And so, yeah, 100,000 is small compared to 2 billion, right? A few orders of magnitude between those two. So we can approximate this with a 0. And we can say that about half the values will satisfy the inner predicate. So given all of this, that turns out to be about 1 and 2 to the 33, right? Because half the value, so this time we're adding the bit, or about 1 in 8 times 10 to the ninth, or 8 billion. So it's unlikely, unless we run like a significant fraction of 8 billion tests, 8 billion random tests, that we'll ever encounter this case. We have to get lucky, right? We have to choose this. We have to pick that. And we might pick this, but then pick a Y that results in a Z that's the wrong size and it fails. Can we get it from path coverage? Can we find it using path coverage? So we're sort of going off into a testing rant here, but I think it's worth thinking about this, how we would find this bug. Path coverage works way better. Path coverage actually is us sneaking up on symbolic execution. We're sort of sneaking up on this by saying, what are the different paths? Well, here, 2 things can happen. I could have X is equal to 100,000, or I could have X is not equal to 100,000, right? And you see that reflected over here. X is equal to 100,000, or X is not equal to 100,000. That's like that first little predicate. This could be our P, right? And for the inner one, we have X is less than Z, or X is greater than or equal to Z, and you see that reflected over here. So we wind up with these little expressions, which look for all the world like the kind of things we were just manipulating in Z3. And so we wind up with these guys. And in this case, path coverage is pretty easy. We would try something with all of these. The idea being that it wouldn't necessarily expose all the errors, but it does lead to us covering some subset of the paths. And if you want to know what that is, there's a whole set of literature about that. Basically, you could imagine all the execution traces of a program. You partition the execution traces, and then you choose the smallest, you choose the least representative out of the lattice from each one, and that gives you a particular path, and you wind up with something like this. And if you don't care about all the theory behind it, this is good enough. It's not all the paths, right? Because there are loops. There can be loops in programs. And how many times do I go around the loop to find a bug? In this case, they're not, so we're pretty exhaustive. We can use a tool like Z3 to generate a specific case for each of these. So I can have X and Y be int X and int Y, and this is perfectly valid Python. Python has a lot of little neat shortcuts in it. X and Y, it's a little pair, and I can assign it a pair. In this case, I assign it these, and I wind up with 2 integer variables X and Y. I make a solver. I say that X has to be 100,000. And I say that X has to be less than 2 times Y, right? Why not Z? I could have used Z. I could have said, there's an int Z. Z is equal to 2 times Y. I have to add that as a condition. And then I would wind up with this. Either way, I'd wind up with the same expression. This is just a little shorter. I can check that satisfiable. Ooh, that means I can, in fact, get a model, which I do. And in this case, it gives me this model. It says, okay, set Y equal to 50,001 and set X equal to 100,000. Does that work? Well, it certainly satisfies this. X is 100,000. If Y is 50,001, then Z is 100,002, which is greater than 100,000. And so, yep, it does. For a large program, trying to cover all the paths becomes problematic for the reasons we just talked about. And so ideally, you would do things like test boundary values, account for overflows, underflows, truncation, so on. right? Because imagine you're trying to get all the different paths through the program, and you hit an add instruction, and you think, well, an add instruction doesn't contribute to the path. It just, adds some numbers. Well, it might, right? It's going to set flags, and it's going to set a value that might be referenced later on. So I have to think about the potential different ways in which add could, for example, set flags as potential different execution paths. So it can become quite complicated quite fast. So pretty quickly, we wind up at the need to think about all of these things symbolically and to execute the program, and I'll put execute in quotation marks, symbolically instead of running it on concrete values like we just ran it earlier. And that's symbolic execution, right? I'm running the program on symbolic X and Y as opposed to on the real X and Y, and I'm trying to build an expression for X and Y based on how the program executes. And along the way, I can attach constraints to them, right? So I might say, well, it's just, here is just X. And this doesn't mention X, so it's still just X. But here it says X is equal to 100,000. And so within the scope of this if, I know that X is 100,000. And within the scope of this if, I know that Z is greater than 100,000, right? So I can wind up with constraints associated with them, but it's still just an X and a symbolic X and Y. And you can use the way you typically would do this kind of thing is you'd use a term rewriter. Some common ones are mod, which is one I really like, but has some issues. Another one is cock, which is used to prove some things about, actually a lot of things, about the correctness of the Da Vinci surgical robot. So if you're gonna have a robot cutting into you, it would be nice to know that the software works well. And Yanni Kouskalos, who used to be at the Applied Physics Lab up at Johns Hopkins, a buddy of mine, did a lot of work on using cock to prove things about the code that was part of the Da Vinci surgical robot. He published a lot of interesting papers about it. So we wind up with symbolic expressions instead of actual values, and we can think of that when we've kind of been doing some of that by building trace tables. Trace tables are sort of a form of symbolic execution. It tends to generate a tree structure when you have branches and loops, right? Because either we take this or we don't. And so I have this division right here, this branch, and the same thing down here with this next if, with a loop, have the same kind of thing happening. And this kind of expansion, right, this branching can become problematic when I have a big program. So imagine that I'm doing this for the executable for, let's say, Portal 3 or Half-Life 3, right? Big video game, which we can presume is going to be huge because it doesn't exist yet. But I'm doing that for one of these. I have all of these different conditions that branch out. And not only that, but this large set of branches exists inside of loops. And so do I have to, multiply the branches every time through, or it becomes combinatorial? And so this can just explode, right? The set of branches I have to deal with can explode for large programs. And so most of the techniques for symbolic execution actually end up, the symbolic part's the easy part. There are tools you use. Most of them focus on how I can prune the tree, how I can aggressively throw stuff away, right? A huge amount, again, of program analysis, reverse engineering, or engineering generally, is figuring out what you can ignore or throw away, right? Because what is the essential complexity versus the accidental complexity? And let's try to focus on the former and ignore the accidental stuff. For the program right, it was easy, but it's not always going to be easy. So here's what that little tree looks like for this program. Instead of talking about trees in some hypothetical way, let's actually look at one. So we have this statement, and then we can have X is 100,000 or X is not 100,000. In this case, we terminate, so we're done. In this case, we have to consider the inner predicate, and we might have this case or this case. In this case, we terminate and we're done. But in this one, we get the assertion. And we can build the path to that by joining the predicates along that path, right? So I have Z1 is 2 times Y 0, and X sub 0 is 100,000, and X sub 0 is less than Z sub 1. Do you see what I did? I did SSA, right? Here is my Z0 is my initial Z. I replaced it with this, so I call it Z1. So you do SSA so that you can now talk about values consistently, right? So they're not changing. And once you have that, then you can join these and wind up with something like this here at the bottom. This is the predicate that tells me the conditions under which this assertion is reached. Great. So now I have something that I can plug into like an SMT solver and try to turn the crank and get an answer for, and the answer will come back to me in terms of X and Z and maybe Y, probably X and Y, because Z is totally dependent on that. And so given that, you can turn the crank by hand. In this case, we do, right? We could derive from this. How did I get from here to here? Well, this atom is still here. This is not, and this is not, because those two got combined, right? This says X0 is less than Z1. This says X0 is equal to this. So I'll just plug this in here, and there we go. And this is Z1, and that's Z1. So I'll just replace this with this, and there you go. And then I can divide both sides by 2, and I wind up with this expression right here. And so an interesting question that you should be asking yourself, this all sounded really plausible, right? And this is how math works. Is this statement true? Is it true? No, it's not true. Of course it's not, because it's computer science. Everything is terrible. And the reason it's not is because we haven't considered 2's complement arithmetic. I did multiplication up here. I could have wrapped around or done some other crazy thing, right? So we have to think about that. It's just hurts my brain. How could that go wrong? Well, suppose I have the int value here, and I take this, when I multiply this value by 2, I get that. Wow, that number is crazy. And I can figure it out by using something like this. And so when I multiply this by 2, a multiplication by 2 is a left shift by 1 bit, which means the sign bit falls off, unless I do sign multiplication. And there we go. So when you're choosing tools, it's important that the term rewriter or the theorem prover that you use understand this kind of thing. And we tried hard to use mod for one of the projects we worked on. Mod does not understand this, right? It assumes that when I add, let's say when I add 1 to an integer, I get a larger integer. In the world of computers, that's not true, right? It assumes when you negate something, you get a different value. In the world of computer integers, that's not true. It's just weird boundary cases, and those will eventually get you. All right. Whew. So suppose you already know about the error. Right? You can look at the program and go, hey, that's an assertion right there. That might be an error. I should look for how that gets there. So you want to generate input that reaches the error. So here's where you are so far. I can run it, and that will take me a long time because I've got to run billions of test cases to be sure that I find the error. And even then I basically have to exhaustively run what was it, 8 billion cases, and I don't want to do that. I could symbolically execute it, but I have problems with the branching logic in programs getting out of hand. So symbolic execution is complicated, but it can tell you about any execution. Concrete execution is simple, but it can only tell you about a specific execution. So wouldn't it be great if we could plug those two together and have both concrete and symbolic execution? And because it's computer science, we'll just combine those words and call it concolic execution. So concolic execution is a portmanteau of symbolic and concrete execution. And what does that look like? Good question. We're going to talk about that next time. So that takes us up to where we're going to start on concurrent execution. There's new homework. Everybody loves new homework. The new homework is should be a really easy extension of what you've already done. I'm hoping. I hope. Should be. So starting with your or my solution to either blocks or to graph, or both, or yours, whatever one you are comfortable with. Build two new data structures. I want you to build something that holds an if then else and something that holds a sequence. Right? These could be classes that you make instances of, or this could be like a tuple, and this could be a list. I don't care. Just build an appropriate data structure to hold those. An if then else is going to hold a basic block that ends in a true or false branch. You should already know how to find those because those are the things that had two exit lines in your previous program. A sequence is just going to hold a sequence of instructions. And for each basic block you found, create one of these two. At the end of each block, or as the then or else part, write out a label setting of this form. So this is harking back to the program structuring stuff, which is where we've been driving the whole time. So use L for your label, set it equal to some address. What is this? This is the next address, right? So in the graph you just built, this was the thing, this was the termination point of your edge. And you either had one, or you had two, or you had none. Okay. We'll come to none in just a moment. Keep track of the number of times a label is referenced. So for each one of these, every time you reference it, you can just bump a counter. And for each structure you get out, print the structure. If the block reaches a return or a return from interrupt or a halt, then treat the next address as 0. So you'd set L equal to 0. That's what we did for the exit case for our back in the structuring days, remember. If a block ends with an unknown address like jump EAX, where is that going? Or jump RAX, I guess. That would be better because it's 64 bits. Jump RAX. I don't know where that goes. I'm going to treat that as an exit. Just go ahead and treat it as 0 to simplify things. And name your new program flow.py. What is this going to look like when you print it out? It's going to look like this. So here's an if then else. So here's my basic block inside here. At the end, I have a jump if equal to 5A70. And so my then part is going to be setting L to 5A70. What about the else part? Well, that's going to be 5A55 plus the 2 bytes for that branch. So that's going to be 5A57. And that's what it is right here. And that's it. If, then, else, phi, because everyone loves the language PL1 or bash. Think of bash. For a sequence, that's really easy, right? I just have, here's my basic block. What happens next is at the end of this, I jump to 50ED. And so I just say L is 50ED. So you're not nesting them yet, but you're going to be. That's what you got to do next. So the next homework, you're going to be beginning to merge these, right? So if you have a 5A70, and for the sake of argument, pretend this was 5A70, you would want to be able to take this and plug it in here. And that would create a nesting. And so you'd keep track of, you should go ahead and as you're writing the code, you should think about keeping track of nesting depth and indenting your code in 2 spaces because it can get pretty deep. So the label settings, this is what they should look like. And the next time we're going to be substituting basic blocks for labels. So consider that when you design your data structures. The then and else parts of an if then else will be replaced with structures. And if it turns out this guy right here, 50ED, was itself a little sequence, I might just merge the two. And so I'd have a long sequence with the label at the end. Things to think about. That's the homework. Next time, we're going to finally get back into, we're going to get into concurrent execution in more gory, gruesome detail. We're running out of time. That's just the way nature of the beast. There's always a lot more we could be doing, but it takes a long time to get up to speed on assembly and how stuff links and how it works and all the other pieces that you need to know.